This marks the continuation of last class, algebraic identities. Before we start, let's write them out. Under expansion, we have four. So we have square of sum, square of difference, cube of sum, and cube of difference. So what are the formulas? For the first one, it is a squared plus 2ab plus b squared. The next one is a squared minus 2ab plus b squared. The third one, a cube plus 3a squared b plus 3ab squared plus b cube. And the fourth one is a cube minus 3a squared b plus 3ab squared minus b cube. You have to know this by heart. This is for the expansion. Let's go for the factorization formula. So we have difference of two squares, sum of two squares, sum of two cubes, difference of two cubes. So what will the answer for this? The answer is a minus b, a plus b. For this, it has to, it's either it's a plus b all squared minus 2ab, or a minus b all squared plus 2ab. For this one, we have a plus b into a squared minus ab plus b squared, or a plus b all cubed minus 3ab a plus b. For this one, a minus b, a squared plus ab plus b squared, or a minus b cubed plus 3ab a minus b. So you have to know everything here by heart. And I said last class, one of the most important under factorization is difference of two squares. So for today's class, we'll focus on using this identity to solve several problems. Difference of two squares. What's the rule again? A squared minus b squared equals to a minus b, a plus b. Now let's solve question. Let us start with these simple questions first. For this first one, we don't need to go far. It's very obvious here that a is x and b is y. So we'll come here, we replace a here with x and b with y. And that's all. For the second one, we can still express this as x squared minus 1 squared. Why? Because 1 squared is still 1. So from here, it means x squared minus 1 squared. Following simply we have here, we subtract x minus 1, then we add x plus 1 for an answer. The next one, I can write 4 as 2 squared, then it means from here 2 squared minus y squared becomes, if you expand, you subtract 4 is 2 minus y, 2 plus y. Then for the next one, I can write this one as 1 squared. Then 4 is 2 squared. So if I have 4a squared, I can write 4 as 2 squared a squared. The square is common, that's 2a all squared. So minus 2a all squared. Now in this case, what happens here? We have 1 minus 2a. Then you have what to add? 1 plus 2a. So if you expand this, you get this. If you check this next one, 2 is not a perfect square, 50 is not a perfect square, although 2 is an even number, so it means 2 is common. If we factorize 2, we left it 1 minus 25p squared. Then we can continue to say this is 2 into 1 squared minus 5p all squared. Why? 25p squared can be written as 5 squared p squared. The square is common, that is 5p all squared. Then what next? The 2 remains outside. Then since they both carry square, so the first is to subtract 1 minus 5p. Then we add 1 plus 5p. So the expansion of this gives this. The expansion of this gives this. If you expand this, you get this. If you expand this, you get this. If you expand this, you get this. So know these 5 simple examples, then let's take more. Okay, let's consider the following question. The first one here. We'll start saying, if you notice 3 and 27 are not perfect squared, but 3 is a common factor. So this can be written as 3 into p squared minus 9 q squared. And this implies that from here we have 3 into p squared. 9 is 3, right? So this is minus 3q all squared. So what next? The 3 remains outside. Now they are both proper squared. P squared, 3q squared. So subtract p minus 3q, p plus 3q. Done. For the next one, 4 is a perfect square. So we can write this as a squared minus 2 squared b plus c all squared. This square is common, so we have a squared minus 2b plus c all squared. You have to ensure that there is nothing outside or beside what carries the square. So what next? We cannot follow the rule straight. We subtract, then we add. So by subtraction we have a minus 2 into b plus c. Then we add a plus 2 into b plus c. By the time we expand, so for this one, I'll be having a minus times b minus 2b minus 2c. Then I'll be having a plus 2b plus 2c. That's the answer. For the next one, when we look at it normally, it doesn't look like difference of two squares, but we know that we can write this as p squared all squared minus q squared all squared. We didn't change anything according to law of indices. Now our focus is the square outside here. The numbers inside are both p squared and q squared. So we subtract p squared and q squared, and we add p squared and q squared. Normally we could have stopped here, but if you notice, this cannot be factorized further. But for this, it has a factor because this is another difference of two squares. If you have a squared minus b squared, the answer is a minus b plus b. If I have p squared minus q squared, the answer is what? P minus q, p plus q. Then we have what there? P squared plus q squared. So this is what the most simplified form of this. So it means p raised to power 4 minus q raised to power 4 has 3 factors: p minus q, p plus q, and p squared plus q squared. Let's move to the fourth one here. So same way, before I can apply difference of 2 squared, what outside must be 2. So for this case, we are having x raised to power 6. So I can write that as x cubed all squared minus y cubed all squared. Now by applying difference of 2 squares, the number inside are x cubed, y cubed. So subtract x cubed minus y cubed. Then we add x cubed plus y cubed. Yes, we've used difference of 2 squared, but we are not done. So what is x cubed minus y cubed? Difference of 2 cubes. Use it here. So for this one, this same thing as, then x minus y cubed is what? X minus y. Then x squared plus xy plus y squared. From where? From difference of 2 cubes. So we apply that identity. For the second one, sum of 2 cubes. Sum of 2 cubes, then we add, we have x plus y. Then we are having x squared minus xy plus y squared. And that will be it. So from here, we can try to write this further by saying, we can write this one first. That's x minus y. Then write this one x plus y. Then write this one. Okay, let's write this one first. X squared minus xy plus y squared. Then this one x squared plus xy plus y squared. So we are done factorizing. So it means x raised to power 6 minus y raised to power 6 has 4 factors. X minus y can divide this, x plus y can divide this, x squared minus xy plus y can divide it. Likewise, what? This can also divide it. So these are called factorization. We can go on and on. You also have x raised to the power 4, x to the power of 8 minus y to the power of 8. Following the same approach by putting square here, by the time you simplify, you get something. Well, that's why all these identities, they are very, very important. Now, recall, I said something about this one having no factors. P squared, q squared, that's sum of 2 squares. If you check, when we added sum of 2 squares here, this is all we add. We have this minus. So this, when you say factors, they are numbers you multiply to get the number. For example, the factors of 10 can be 5 times 2. Right, 5 times 2. So 5 can divide 10 and 2 can divide 10. But there is no number that can divide this. But for a cube plus b cube, this and this are the factors. A plus b can divide a cube plus b cube, while this other part can also divide this. But this one is not in terms of factor. So we've applied this one already to solve question in our previous lesson using under the sum and product of what? Quadratic root. And I believe with this example, we should be able to solve any question regarding the difference of two squares. Let's solve more questions. Consider this question from ETM 1989 or 21. We are told to factorize this. So when you look at this initially, it doesn't look like difference of two squares. Yes. But if we check very well, we have A, we have B, we have AB. C is 0, don't stand alone with no other out. C. A, B, AB. So this means here we have perfect square. Listen, when we talk about difference of two squares, it means you have two perfect squares. Let's rearrange first. So this can be written as 4a squared minus 12ab plus 9b squared. It makes sense because they all have something in common. Then minus c squared. Now, if you observe very well, everything we have here can be expressed as a perfect square. It's either you consider this as a quadratic expression that is simplified, or we try to use what? Square of sum. And here, this 4a squared can be expressed as 2a all squared. This 9b can be expressed as 3b all squared. So at the center we have twice minus what? We have ab. We have ab. What else beside ab? 12. And what's 12? 2 times 6. 2 times 6. So we can say 2 into 6ab. That is everything we have there. Why am I doing this? What do you have here? You have square of a number, square of another number, and the center is what? Minus twice their product. If I do 2a times 3b, I'll get 6ab. If I do 8 times b, I'll get ab. So it means this is a perfect square. We can write this as 2a minus 3b all squared minus c squared. If we expand this, we get this. Sorry, I was pointing at this. It actually falls under this square of difference. Why? The center is negative. The center is negative. If we expand this, we get this. Although, if it might be difficult for sometimes to see that we can write this one in this form. So what are you going to do? You can solve it like a quadratic equation. In our last two classes, we solved similar question. When we have a quadratic expression that look in this form, that look at that form with already solved question on it. Okay, let's look into this in another way. We have 4a squared minus 12ab minus 9b squared. We don't want to manipulate. Let's solve.